It's my great pleasure to introduce a friend and longtime collaborator, Kathryn Hess, who's going to tell us about cubes, comonads, and calculus.
Thank you very much, Ron. I would have loved to be with you today. I have great memories of the conferences that I attended at Sky. It's a great privilege to have been invited. So the work I'm going to talk about today, there we go, is, it started a long time ago in discussions with Brenda Johnson. Indeed, the last time I was at Sky, which I guess was in 2009, I was there with Brenda, and we were already starting to talk about some of the things I'm going to be presenting today, although it was nowhere near the sort of form I'm going to be presenting it in. And then it was work that continued last summer in a project in the 4th Women in Topology workshop, together with Brenda, but also Christine Bauer, Robin Brooks, Julie Rasmussen, and Bridget Schreiner. So this is going to be resuming the work done by all of us together, and in large part based on the work that Brenda and I did. So I'm going to start by talking about what is a calculus or a cocalculus in general, and then talk about how we can go from comonads to calculus and the dual, from monads to cocalculus. And I'll explain on the way what monads and comonads are, because I know this is a very mixed audience. And talk about how we can go from cubical structures to comonads, which will then enable us to put it all together and go from cubes to comonads to calculus in a way that gives us a whole range of different calculi that are possible for functor categories, which is sort of one of the main places where one applies calculus to analyzing functor categories. So let's dive right into it. What in the world is a calculus or a cocalculus in general? The idea here is I'm going to abstract from the usual notions of functor calculus or notions of orthogonal calculus or manifold calculus. There are lots of different ways one can think about different theories of calculus that have been developed, and try to sort of abstract from that and get to the core of what a calculus, cocalculus is. So the context is the following. We start with some category M, equipped with some distinguished class of morphisms, which we call weak equivalences, WE. And I'm going to consider one object in the category M. And what I'm going to have in the calculus is a sequence of approximations to my object X. In order to understand in what sense it's an approximation, I need to have a morphism that connects X to each of these approximations, X0, X1, X2, and so on, all the way up. And the idea is that each successive map from X to Xn should be sort of increasingly good approximations or increasingly close to being a weak equivalent. Sense. And then the morphism from X to Xn, we'll think of some sort of degree and approximation here. The idea here is thinking about some sort of an analog of taking Taylor polynomial approximations to functions and so on, where we're doing finer and finer approximations as we go up this tower. So this is one sort of form that a calculus will take, where, for example, M would be some functor category and X would be some functor in that functor category. But we can apply it in general in any category where there's some good notion of weak equivalences. Cocalculus will dualize this. So in the dual context, we'll instead have maps going up instead of going down. So we'll go from X0 to X1 to X2 and so on, and then be mapping out of the Xn to the X, and so some sort of co-degree n approximation. And these should also be increasingly good approximations in some sense that depends on the context. It depends on what your category M is, what your weak equivalences actually look like, in what sense it makes sense to talk about being an increasingly good approximation to a weak equivalence. So what are the fundamental underlying structures that we're looking at here? When we're thinking about a calculus, we're thinking about a sort of a notion of a co-augmented tower in a category. So if we have a category A, and then we can look at the category, let's put my cursor over here if I can. I'm having trouble doing that. Okay, so the category A, and we can look at a category of towers, of actually co-augmented towers in this category A. And so what is this? It gives us, we have these towers of morphisms, P1 from A1 to A0, P2 from A2 to A1, and so on. And then for some fixed object, little a and A, we have a collection of maps, F0, F1, F2, and so on, that are mapping into that. That's exactly the sort of structure we were seeing in the the informal presentation of what a calculus might be in a category equipped with weak equivalences. And then if we're thinking about a co-calculus, then we have augmented, well, let's call them co-towers. One could also call them telescopes, because now we have our maps with the indices going up. And now we're mapping from each of the AIs to A itself. So this is the dual kind of structure that we were seeing in the context of what a co-calculus would be. So now those are sort of it's a categorical framework for the sort of structures that appear when we're thinking about the calculus or a co-calculus. So now if we think about how can we actually formulate what a calculus or co-calculus should be, then what we're thinking about are certain kinds of functors. Now we have a B, which is going to be a subcategory of our category A that we had. And we're going to look at a functor gamma from the category B to the category of these co-augmented towers in A, so that it's going to send an object little b to one of these co-augmented towers where you're co-augmenting from the object little b to some sort of tower. And you're looking at these gamma k of b's as being successive approximations, or that's one way you might like to set it up, for your object B. And so and then the etas are giving you the successive approximation maps from B to each of the gamma k of B's. And so you have this whole coherent co-augmented tower like this. So we're getting closer to really defining more formally what we could think of as a calculus in this sense. And of course, there's a dual framework where again, we have B, which is a subcategory of A. And now we're looking at a functor phi from the category B to the category of these augmented cotowers. So now we have each of the phi k of b's is we could think of as some sort of approximation to the object B, and they come equipped with maps to the object of interest, which is the object little b. So now that we have an appropriate categorical language in which to talk about the sort of formulation of calculus or co-calculus, let's go back and think about, all right, let's make this more formal. Okay, so now we're in a situation, we're back to a situation where we have a category M equipped with some collection of weak equivalences. And now I'm going to fix some subcategory in M prime, where the objects are of particular interest or particularly easy to work with, or for some reason I want to focus on some subcategory of M. And then what I'll call a calculus on M prime, this subcategory, with values in the category M, is now going to be one of these tower functors from M prime to the augmented towers in M that is going to satisfy certain nice homotopical properties. So let's look at the first one. If I have little m as it is less than or equal to little n, then I'm going to say, okay, if I take the map eta n of x, which goes from x to gamma n of x. I'm thinking of gamma n of x as being some sort of degree n approximation. Think about it as some sort of polynomial approximation of degree at most n. Now, suppose that I take that degree n approximation and I apply a degree m approximation to it, where m is less than n. So now I'm cutting off the parts of the polynomial of degree greater than m. Well, it makes sense that if I do that to x itself, or I apply it to what I've already done as the degree n approximation, what I should get should be equivalent in this case, because m is less than or equal to n. Similarly, if I take the degree m approximation, so I have now, I think about it, the polynomial approximation of a polynomial degree at most m, and I take a degree n approximation of that, where n is greater than or equal to m, that's not going to change the degree m approximation. You don't have any higher terms. So it makes sense that you should have an induced equivalence from gamma m of x to gamma n, the nth approximation of the nth approximation of x. And moreover, because we are in a world where there are weak equivalences, and so we'd like that sort of thing to be preserved, we would like gamma n to preserve weak equivalences for all n. And this is sort of what you could call a very bare bones definition of what you could call a calculus in this context. Where this all makes sense with this kind of motivation, again, of thinking about these things as actually being polynomial approximations of different degrees. And we can formulate an analogous definition for a co-calculus. So I'm just going to display it all at once here. So again, we have our category M with its weak equivalences. We look at some particular subcategory M prime. And now we're going to have one of these cotower functors from M prime to the cotower. And now we have these epsilon maps. The epsilon n of x goes from phi n of x to x. And again, it's the same sort of thing that if we've already taken some sort of degree n approximation, and then we take a degree m approximation of that, it should be the same thing as just taking the degree m approximation, as long as m is less than or equal to n. So these conditions are analogous to what we had in the dual case. And again, it makes sense because we're working in this context where weak equivalences play an important role, that we want the phi n's to preserve weak equivalences for all n. So this is just purely dual to the previous definition of a calculus. So once we've done this, we can say, does this definition actually behave well with respect to the sort of things we usually care about? When we think about taking Taylor approximations and so on, we say, okay, does the sequence of Taylor approximations converge in some sense to the original function that you started with? And so how can one formulate questions of convergence in this context? So again, I have my category M with weak equivalences, subcategory M prime. I fixed an object in M prime. And suppose I have a calculus. So this is one of these tower functors from M prime to the augmented towers in M, satisfying these conditions about degree M and degree N approximations playing nicely together. So suppose that this category, in addition to having weak equivalences, has a reasonable definition of homotopy limits. So maybe we're in a model category, and so we know how to define homotopy limits. And then we would say that the tower gamma of X converges to X when the induced map from X into the homotopy limit of the tower, you go all the way to the top of the tower, is actually going to be a weak equivalence. On the other hand, you can say, okay, how about a cocalculus? Well, we have a cocalculus, and we have a more of a telescope thing. And if now your category admits homotopy co-limits, then we'll say that this co-tower converges to X. When you take the homotopy co-limit of this tower, you end up with something that's weakly equivalent to X, so that you have this induced map out of the homotopy co-limit, and that should be equivalent to the object that you started with. So we have a reasonable notion of convergence that fits with the notions of convergence in sort of more classical calculus. But when we're in a context, again, when there are weak equivalences, often, one of the important cases we care about is when we're looking at functors out of some category that's equipped with weak equivalences into some other category that's equipped with weak equivalences. So here we have M and C. And if we're thinking about a calculus that's actually on this functor category, so we have some distinguished class of functors from C to M that do something nice. And if we have a calculus like that, so that's going to be one of these tower functors from this subcategory of functors to the towers of functors, now functors and natural transformations, that this is going to be a homotopy calculus if whenever we take a functor f that preserves weak equivalences, so f is a functor from C to n, that sends weak equivalences in C to weak equivalences in M, that every layer of the tower that we get, so every gamma n of f, should also have this property. It's a reasonable thing to ask for in most homotopy theoretic contexts. And one can say something dual in for the homotopy co-calculus, that as like we have a functor from C to N that preserves weak equivalences, then every level in the co-tower that we have, so every phi n of f, should also preserve these weak equivalences. So the goal of the presentation today is to give you a description of a functorial pipeline for creating calculi, homotopy co-calculi for functor categories in particular. So one reason it's interesting to have a functorial pipeline like this is it's going to give you ways of playing with coming up with a whole range of possible definitions of calculus, which is going to give you a range of different notions of what it means to have a degree n approximation or a co-degree n approximation of a functor, which can be useful for examining functors from different perspectives. One reason one can be interested in looking at something like this is for determining, if you know that if you're looking at two different objects in your category that on which you have a calculus, to determine whether or not the morphism between them is actually equivalent, you can sort of start looking at what's induced and between the approximations as you go up. So being able to have a number of different perspectives from which you can look at things and having everything being natural so that there are all sorts of comparisons you can make is one of the reasons, is the main reason why we were interested in having this very functorial approach to creating a whole family, a spectrum of different calculi and co-calculi. But before we do that, let's just look at a couple of properties of these calculi and cocalculi and see that whether it makes sense, whether it sort of fits with what we would hope for in this context. So in terms of properties, let's suppose we have a calculus again. So we have a category M equipped with weak equivalences. M prime is a subcategory of M. And we're going to fix some object in M prime. And we'll say it is gamma degree, so it's its degree with respect to this particular choice of a calculus, is less than or equal to n, if it's weakly equivalent to this sort of nth approximation, so to gamma n of x. So that doesn't mean it's not weakly equivalent to gamma m of x for m less than or equal, but at least it's equivalent to gamma n of x. And then, indeed, it's not hard to show. It's an easy exercise to show that if x is a gamma degree m, then it's of gamma degree n for every n greater than or equal to n. So once you are equivalent, you're equivalent. And now suppose that our category is pointed, and so that we can have some notion of what a base point object is in the category. And we'll say that our object is homogeneous of gamma degree n if it's of gamma degree n. And indeed, its n minus first approximation is trivial. So in some sense, it's really sort of concentrated in gamma degree n. We're interested in the objects that are homogeneous of gamma degree n. We can think of them like monomials, like x to the power n or something like that. And see they're sort of fundamental building blocks of the objects in my category. That's why I'm interested in them. So how can I produce objects that are homogeneous of a particular gamma degree? So one thing we can do is to look at the difference that there is between gamma n of x and gamma n minus 1 of x. These two are linked in the tower. And if I have some notion of homotopy fiber, so now I'm supposing anyway that I have a base point, and if I have some way of taking a homotopy fiber of the map from gamma n of x to gamma n minus 1 of x, I'm looking at the difference between these two. It's what I'm measuring with this homotopy fiber. And so you're just picking out what is the new bit that I added when I went from the n minus first approximation to the n. And so I can calculate this n layer functor. And it turns out that under reasonable conditions on gamma, which I'm not going to go into today, particularly since we have a mixed audience, not only algebraic topologists, it turns out that this nth layer functor actually does give us an object that is n homogeneous. That's a way of picking out really these sort of building block pieces. And that if I take the map that's giving me the nth approximation, so a to n of x from x to gamma n of x, and I apply this nth layer functor, that it really does give me a weak equivalence, which is what I would expect, that the nth layer of x is equivalent to the nth layer of gamma n of x. Okay, so that's some basic properties of the calculi. Let's just see a couple of examples just to show that these things actually do exist and correspond to things that are very common actually on a daily basis. So the first one is called the Polytechnique calculus. So this is going to be some tower functor gamma from the category of topological spaces to the category of co-augmented towers in topological spaces. And we're thinking about the category of topological spaces as being equipped with the usual notion of weak homotopy equivalences for the weak equivalences. And the tower that we're going to build is a tower that's the Polytechnique tower of x. So the gamma n of x is just going to be an Polytechnique section of x. So that it's going to have all the homotopy groups of x up through degree n, and then have 0 homotopy groups above. So we definitely have this idea of a better and better approximation to x. And in this context, having gamma degree of x less than or equal to n means that the homotopy groups of x above degree n are all trivial. And the nth layer functor is nothing but an Eilenberg-MacLane space. So this is really, sort of an example of what we could think of as a calculus of this way. We can also do an algebraic version of this as follows. So let's call it sort of the algebraic Polytechnique calculus. So in this case, I'm going to apply a functor to the category of non-negatively graded chain complexes over a commutative ring R, where I'm going to consider as equipped with a projective model structure. The most important thing are the weak equivalences. So these are just going to be quasi-isomorphisms of chain complexes. So this is one of these tower functors from chain complexes to the category of co-augmented towers in chain complexes, which is defined as follows. So if I have a chain complex XD, I'm going to, when I take gamma n of it, it's going to stay the same up through degree n. In degree n minus 1, I'm going to quotient xn plus 1 by the kernel of its boundary map, and have 0 above. Then there's an induced differential here. This is a quotient, in fact, of xd, and gamma n minus 1 is a quotient of gamma n. So that the maps in the tower, eta n, is just going to be the quotient map from xd to gamma xd. And gamma n is also going to be a quotient map. And so that gives me an entire co-augmented tower in this way. And is this some kind of calculus? If so, what does it look like? It does indeed give me a calculus. And what we see is that if I calculate the homology groups of gamma n of x are the same as the homology groups of x to degree n and 0 above, the gamma degree of x being less equal to n just means that its homology group is 0 above degree n. And the homology, we can again compute this layer functor, and we see what it means to be homogeneous. Gamma degree n means the homology is concentrated in degree n, and indeed it picks out exactly the nth homology group of x. So this is an algebraic analog of what we saw for topological spaces. Okay, so that's the basic idea of a calculus with a few examples and some properties. So now, how can we create things like this? How can we build tower functors, co-tower functors that satisfy the right kind of properties? That's what we're going to do next. I'm going to show how we can use comonads to build calculi and monads to build cocalculi. But I'm not going to assume you necessarily know or are comfortable with monads and comonads. We're going to start by talking about what those are. So now we're just going to take any old category A and think about the notion of what it means to have a monad on A or a comonad on A. So we start in both cases with an endofunctor in the category A. We'll call our monad the underlying endofunctor for a monad T, the underlying endofunctor for a comonad K. And then for our monad, we have a natural transformation mu from T composed with T to C, T squared to C. And we have a unit natural transformation from the identity functor on the category A to the functor T. Okay, so the comonad is the dual. We have natural transformation from the endofunctor K to K composed with K. And we have a co-augmentation from K to the identity functor on A. Now, obviously, these should satisfy certain axioms. One is an associativity for mu or a co-associativity for K. The two different ways of getting from T cubed to T or from K to K cubed are the same. And also unitality or co-unitality property, saying that if I apply the unit in one factor and I then multiply, it's the identity or and dually for the co-unit or the co-notation. So one short way of saying this is that a monad is a monoid in the category of endofunctors on A equipped with composition and dually for comonads. So why do we care about monads and comonads? First of all, where do they come from? A great source of monads and comonads is adjunction. So suppose I have an adjunction, it's up there on the upper right-hand corner where I have two categories A and B, and I have functors L and R that are left and right adjoint respectively between these two functors. From that, I can build a monad on A. If I look at the composite RL, it's an endofunctor from A to A. If I take the composite RL, I can use the co-augmentation of the adjunction to give me a map from RL to RL. And the unit of the adjunction is going to be the unit of my monad. Dually, for the comonad, I can take the composite LR. I can use the augmented, so the unit of the adjunction to give me a map from LR to LR. And the co-unit of the adjunction is going to be the co-unit of the comonad that I get. So this is, it turns out that every monad gives rise to an adjunction, every comonad gives rise to an adjunction, and that there's really this beautiful relationship between adjunctions, monads, and comonads. Now, when one has a monad or a comonad, one can then talk about algebras over the monad or coalgebras over the comonad, and that's the next thing I need to talk about. So now we suppose we have a category, and we look at an object, little a, in this category. And we suppose we have a monad T, and so I'm going to write this bold T to represent the triplet T mu eta, and bold K for the triplet K delta epsilon. And once I have a monad like this, or a comonad, I can define algebras and coalgebras. So a T algebra structure on the object A is just a morphism in the category A from TA to A, satisfying certain properties. And the coalgebra structure is a morphism in the category A from A to KA. And they satisfy associativity and unitality properties. So this is a compatibility between, for example, in the case of the algebra structure M, it's a compatibility between M and the natural transformation mu, because the natural transformation mu, they'll take us from T squared A to TA. And so this is giving us a nice associativity diagram, and we have the unitality condition as well. So there's a lot of interesting things to do studying monads and comonads. Now, I'm going to use this sort of approach and talk about the next thing, which is associating certain simplicial or co-simplicial objects to monads and comonads. This is going to be important for the construction then of a calculus from a comonad or a cocalculus from a monad. So we're still in the situation where we have a category A and we have an object A in the category. And suppose we have our monad T, our comonad K. We can associate to the monad T a certain co-simplicial object in the category A, which I'll call omega dot T of A. Or in the case of the comonad, we can associate a simplicial object to A. It's called the K bar construction, B dot K of A, which are defined as follows. So first of all, what I have in level N of my co-simplicial object is what I get when I apply T n plus 1 times to A, and dually for the bar construction, I apply K n plus 1 times to A. And then the cofaces in the co-simplicial object omega T of A are given by the unit of the monad eta, and the codegeneracies by mu. So you think about how you can, where these maps have to go. You can sort of play a game, and though basically the only way you could do it is what works. I didn't want to go into the details today, but you can really build this whole co-simplicial or simplicial structure using the rest of the structure maps of the monad or the comonad. All right, so where we can go from there? We want to make a few observations about this co-bar construction and this bar construction. And then from there, we're going to be able to take the next step and see how we can start building a calculus from these things. So one thing to note is that there's a map from the object A that we start with into the bottom, either of the co-bar construction or of the bar construction. The omega 0 T of A is just TA, and the unit natural transformation of the monad from the identity to T gives us a morphism in the category A, where we look at the component at A, from A to T of A. Dually, if we look on the comonad side, the co-unit of the comonad from K to the identity on A gives us, when we look at the component at little a morphism from the bottom of this simplicial construction, which is just Ka to A. So what this means is that the co-simplicial object is always co-augmented, and the simplicial object we get is always augmented. Not only that, if we actually have a T algebra structure on the object A, there's a way we can use that multiplication map M to give us what's called an extra codegeneracy in this co-simplicial construction. And dually, if we have a K coalgebraic structure on our object little a, we can use the co-multiplication little d to give us extra degeneracy in the simplicial construction, which means that in fact, if we do have some sort of way we can realize or take a totalization in the case of the co-simplicial object, that we have something that's actually equivalent to A. So this is going to be important for the next point we're going to make. That okay. So suppose now that our category, which is equipped, we're in a category that is actually equipped with weak equivalences, and we have some object in this category. I think I wrote A at the top of the page, but I think it then becomes X. No, it's still A. Okay. So, and we take an object in our category, and what we're going to do now is use these bar and co-bar constructions to measure how far the object A is from being one that one can equip with either an algebra or a coalgebra structure. So what we want to do is take this cosimplicial construction, for example. So we have there omega TA. This is this cosimplicial, the cosimplicial cobar construction on A associated to T. And if we're supposed to have totalizations, totalizations give us a way of taking a cosimplicial object in A and obtaining from that, or in M in this case, and obtaining from that an object in M. So you could map from cosimplicial objects in M to M. So suppose we have a way of doing that. We have this co-augmentation that went from the object little a into the bottom of the cobar construction. And so there's an induced map from little a into the totalization of this cosimplicial construction. That's now a morphism in the category M, of which we can take the homotopy fiber. When we're taking this homotopy fiber, we're measuring the difference between little a and the totalization of the cosimplicial of this cobar construction. Dually, in the case of the comonad, we can look at this simplicial comonad construction. If we suppose we have some way of taking a realization, so we have a functor from simplicial objects in the category M to the category M, then we can take this realization of this simplicial bar construction. It gives us an object in the category M, and the augmentation of the bar construction, which gave us a map from the bar construction to the object little a, will then induce a map in the category M from the realization of the bar construction to A. And then we can take the homotopy co-fiber of that, which is another way of measuring the difference between the geometric realization of the bar construction and A itself. And so what phi t of A and gamma k of A are measuring is, in some sense, how far, what the difference is between A and its either totalization or its geometric realization. And because of the fact that when, for example, A is equipped with a T algebra structure, we know that we have these extra codegeneracies, we know that, in fact, this totalization will give us something equivalent to A. So in other words, what we know is that if A admits a T algebra structure, then this phi t of A is actually going to be trivial, and similarly equivalent to the base point, and similarly for gamma k of A, if A admits a K coalgebra structure. In fact, this thing being trivial is a little, it doesn't imply that you actually have a K coalgebra structure, something a bit weaker, it's some sort of up to homotopy version, but it's sort of like saying how far is it from being something being equipped with a strict algebra or coalgebra structure. So that's what we're measuring here. Okay, now how are we going to use that to get even closer to cocalculi? So here, when we're taking homotopy fibers and homotopy cofibers, that means that we actually have there's going to be a natural map from phi t of A to A, and a natural map from A to gamma k of A. So that's what comes out now, that we have this map from phi t of A to A and from A to gamma k of A. Now this is starting to look like what we would need to have either on the left, the augmentations, or on the right, the co-augmentations for one of these co-towers or towers. And indeed, if we have either a co-tower of monads, I didn't explain what morphisms of monads are, but there's a way of defining this notion. It's some sort of natural transformation that respects what it needs to respect. Or we have a tower of comonads. Again, there's a notion of morphisms of comonads. Then from that, we can actually build either towers, augmented co-towers of objects in M using these associated phi t's that we constructed before. So it's looking at these homotopy fibers of the maps into the totalization of the cobar construction. Or on the other hand, we have, if we apply this to a tower of comonads, let's call it K script K, then it's going to give us now a tower of objects in M, where each of these gamma Ks is coming from looking at the homotopy co-fiber of the map from the realization of bar construction to X. And so it comes with naturally equipped with these maps from X into each of these gamma Ks. And so we have this way of going from either a co-tower of monads to a co-tower, an augmented co-tower of objects in M, or a tower of comonads to a co-augmented tower of objects in M. So now we're in the right categorical framework in any case. And so when is this actually going to give us calculus? So if we have a tower of knights monads. So I'm not going to go into details about what nice is here, the sort of nice homotopical properties behaving nicely with respect to homotopy fibers and geometric realizations and so on. There are ways of setting it up in various model category theoretic contexts, implicit model categories, and so on. We're just going to say nice for today. If you have nice monads, then you actually get a cocalculus out of this. And if you have nice comonads, you actually get a calculus out of this. So this is starting to move in the direction of having a functorial approach of building whole families of calculi and cocalculi. And they say, okay, now as long as I start with some nice collection of monads or comonads, I can get from it a calculus or a cocalculus. And it turns out that if M is actually stable in some standard sense of the word stable, so we're thinking about spectra or unbounded chain complexes or something, and these towers are nice enough, then the layers of these calculi will be homogeneous as we would like. So let's look at an example, something more concrete. So again, back in the world of chain complexes of our commutative ring, and think about an adjunction between chain complexes that are bounded below, so that are 0 below n degree n. And so there's an adjunction where the left adjoint is just the inclusion of the subcategory, and the right adjoint is some appropriate truncation functor. Then this is going to give us a comonad, right? We know that adjunctions give rise to comonads. There's a comonad on the chain complexes on R with underlying functor. There's the composite of iota n with rho n. And then because we have the compatibilities along n, this actually going to give us actually gives rise to a tower of comonads. And from this tower of comonads, we then get a calculus, according to the formula that I explained. And this calculus is exactly, in fact, the calculus that I defined earlier for chain complexes over this particular commutative ring. So this is an effective way of explaining that one of the calculi we already saw that we built by hand is coming from actually a tower of comonads, as I described before. Something that we didn't see yet was to let's start with simplicial abelian groups. Let's consider some set of primes. And let's get from the set of primes a sequence of rings where in ring Rn, we've inverted all the primes pk up to level n. And let's let iota n be the inclusion of the integers into Rn. So there's an associated adjunction to this where the left adjoint is coming from restriction along iota n. And there's an associated comonad in this case. And this is the sequence of comonads, the inclusion of the ring Rn to the ring Rn plus 1 will then induce a morphism of comonads, and we get the whole tower of comonads this way. So building this tower of comonads from some sort of tower of adjunctions, actually. And if we take for M prime the set of all simplicial abelian groups that are actually torsion-free in each level, then the induced tower functor, is indeed a calculus in this case. And what its nth layer detects is the part of the simplicial abelian group that's Pn divisible, but not Pk divisible for any k less than n. So it's a rather complementary sort of calculus that one can build up that I'd never seen before we started sort of playing around and looking for examples that were coming from comonads like this. So to summarize what's in this section, so if we have some category equipped with weak equivalences, and we have some subcategory of this, and suppose that it's, pointed admitting homotopy fibers, homotopy cofibers is necessary, then some nice enough tower of comonads on the category M will give rise to a calculus like this on the category M prime with values in M. And similarly, a nice enough co-tower of monads on M will give rise to a cocalculus on M prime with values in M. So now this begs the question of how do we get monads and comonads, particular towers and co-towers of comonads and monads. So the title of the talk was Cubes, Comonads, and Calculus, and we're sort of doing things backwards. I do calculus and then comonads and finally cubes. And then we'll figure out how we can string them all together to get from cubes to calculus. So from cubes now to monads and comonads. So when I talk about cubes, what do I mean? I'm really thinking about a category that I'm going to call Pn, where n is a natural number. And I'm going to, Pn is just a post set of all subsets of set of numbers from 1 to n. So when n equals 1, okay, it's just the inclusion of the empty set into 1. That's all we have. When n equals 2, now I have a square of sets of morphisms and all the way up. So, for any n, the post set that I have really looks like an n cube. So in particular, if I look at functors out of Pn into some category A, then what I really have are n cubical diagrams in A. So that's anytime we have functors like this, it's a way of thinking about cubes in the category A. But what we're going to need if we want to think about monads and comonads is monoidal structure on the category Pn. So I'm going to be thinking about some functor theta from Pn cross D to D. And I want to think about this as some sort of action of Pn on D. But to talk about action, I need to have some notion of a multiplicative structure on Pn. And there are two obvious ways to do that. One through intersection. Of course, intersection of any two post sets is still a post set, or union. In the case of intersection, the unit is, of course, the set of all the numbers from 1 to n. In the case of union, the unit is, of course, the empty set. And so what does it mean for theta to be a module structure with respect to intersection or module structure with respect to union? Well, there are two conditions. If now I have S and T, which are subsets of the numbers from 1 to n, and D is some object in D, then I know that if I apply theta to TD, and then I apply S, use S, then it should be the same as theta of S intersect T and D, and dually for the union. And that the unit object should have a trivial action on every object in D. So theta n of D is equal to D. In the case of intersection, theta empty set of D is equal to D in the case of union. So how can we understand what these P of n module structures are? There's an interesting characterization, I think, which is the following, which says that a P of n intersection model structure on D is equivalent to specifying n different strict co-localizations of the category. So you have adjunctions like this between some subcategory DG and D, and it's a strict co-localization, meaning that RG over G is really the identity. And all of these co-localizations commute. Dually, in the case of a union model structure, it's equivalent. Defining a union model structure is the same as specifying n strict localizations of the category DG, such that they're all commuting. So what's the interpretation? How do we pass from one to the other? Well, having a functor from P of n cross D to D is the same as having an n cubical diagram in the category of endomorphisms. So these two formulations are equivalent via adjunction. And the fact that theta of empty set D is equal D is saying that theta sharp of the empty set should just be the identity functor. And saying that theta is really an action, that theta S, theta TD is the same as theta S union TD, means that if you run it through, that theta sharp of S union T, well, that'll obviously be theta sharp of T union S because it's strictly symmetric. And so we get in the end that theta sharp of S and theta sharp of T should commute. And what we can deduce from this is, in fact, that this functor theta sharp is going to be completely determined by its values on the singletons. And that's what's giving us, in fact, these different localizations. And so from this analysis, we can deduce that it's enough to specify these n different strictly commuting localizations. So for example, we could take a commutative ring with different subsets of the ring. And from that, we can obtain a theta S that looks like this, where we would do the localization inverting various of the elements in R. And that's just going to correspond to having a collection of these localizations, where Lj is just going to be the localization that's inverting the Sj's. So this is one example of this kind of, we can get there. Of course, this is going to link back to isomorphism. So we'll take it. Okay, so now, how are we going to get from cubes to monads and comonads? Let's start now again with a category that's equipped with some weak equivalences. And suppose we have now a 2 cube, that is to say, a functor from P2 into M. So that's this white corner here, x empty set, x1, x2, and x12. And so if we want to take what's called the iterated cofiber of this cube, we can take the cofibers horizontally and then take the cofiber of the induced vertical map. And that's what's called the iterated cofiber. You could also do it the other way around and end up something equivalent. Dually, you can take the iterated fiber. So you can take the fiber of the map from x1 to x12, the fiber of the map from x empty set to x2, and then you take the fibers vertically and then take the fiber horizontally. And you have this notion of iterated fiber. And again, you can do it the other way as well. But what can be really interesting is to look at this and say, but actually there's an equivalent way to compute this by embedding this cubical diagram, the square diagram, into a bigger diagram of which I take either a homotopy colimit or a homotopy limit. And these are sort of two dual ways of inserting this square diagram into a bigger 3x3 diagram. And that gives you another way of computing the iterated fiber or the iterated cofiber like this. And this gives you an idea of how it is that one can generalize this construction of iterated fiber, iterated cofiber to n greater than 2. The idea is that if we have an n cube, we're going to embed it in something bigger, of which we'll just take either a homotopy limit or a homotopy colimit. So how do we do that? What we think about then is we have a category either lambda over here, which is it's a lambda-shaped category, or V because it's a V-shaped category. And if you think about what it looks like when you take iterated products of lambda or iterated products of V, you're getting these big square diagrams where you have all of the big cubical diagrams where you have either all these arrows pointing in or all these arrows pointing out like this, and which is analogous to the pictures we had before. And then there are ways of embedding Pn into either lambda to the n or V to the n. And the iterated fiber, iterated cofiber are homotopy limits or homotopy colimits over these categories lambda n and vn, where we've done either a right con extension or a left con extension. But if this is a mumbo jumbo to you, then just think this is some sort of higher dimensional generalization of the picture that was on the previous page for n equals 2, just understanding really what's going on there with either doing right or left con extensions. All right, so now that we have these constructions of iterated fibers and iterated cofibers, this is a tool that we need in order to go from actions of P of n to monads or comonads. So let's see first how we can build an n cube from a P of n action, without even thinking about the action part. So suppose we have a category M. We have, now just say a functor, we don't care about whether it's an action for the moment, Pn cross D to D, a functor from D to M, and we're going to fix an object in D. So using theta, F, and D, we can define an n cube, a morphism functor from P of n into M, that's going to send a subset S of the numbers from 1 to n to F of theta of Sd. So theta of Sd is an object in D, we apply F to it, and we get an object in M. So if we look at the case when n is 2, for example, it gives us now a square diagram in M, where we have at each corner F of theta of an appropriate thing, and D. Okay, so now that we have this idea of how to get a cubical diagram from theta, F, and D, we're going to use that to build our monads or comonads. So here's the recipe. We start with some category M equipped with weak equivalences. We start with theta, which is going to be this map again from P of n cross D to D, a functor F from D to M, and an object little d and D. If our theta is now an action with respect to intersection, we can build from it a monad, P theta, on the functor category, the category of functors from D to M, such that if I have this functor F, I apply T theta to it, it should give me another functor. And so I have to say, what do I get when I evaluate this functor on D? Well, it's going to be exactly the iterated cofiber of this diagram, X theta D, that we just defined in the theta Fd that we defined on the previous page. On the other hand, if we have a union action, then we can build from it a comonad, again on the functor category, in the following way. We take our functor F, we apply K theta to it, that's going to give me a new functor in the category from D to M. I apply, and what value do I get when I apply it to D? Will be the iterated fiber of X theta F of D. Where are the monad and comonad structures coming from? The monad structure is coming exactly from the intersection action, and the comonad structure is coming exactly from the union action. So they really have to use this this action structure in order to get either the monad or the comonad structure. So what do we know about these guys? Well, whoops, why is that in there? All the constructions we have here are in fact natural in all the variables. And this is something that I'm sparing you tons of details about what kind of morphisms we're looking at and how to show the naturality, but everything here is natural in whatever you would like. We can also change the source category. So suppose we have some functor S from a category C to D. And we have, if we're given any monad T on functors from D to M, or any monad K on functors from D to M, we have adjunctions that relate functors, the functor category C to M to the functor category from D to M, where this S upper star is just pulling back along S, precomposition with S, lan S is left con extension, ran S is right con extension. And we can build by taking the composite by going over with, for example, left con extension, applying T and coming back with S star, it gives us now a monad on functors from C to M, and dually in the comonad case. So if you're given a monad on functors from D to M, and just some functor from C to D, you can build from that a monad on functors from C to M, and dually. So we can get from this an expression of how we can talk about naturality in this context. So as I was saying, everything was natural. So we have the category with our category M equivalences. We have our theme, I would say any small category, because I'm going to be thinking about functors out of it. And suppose that M has either Hochkommens or homotopy limits, whatever I need, then in fact I can get a functor from the category which has as objects functors from C to D and some sort of intersection action of Pn on D. Or on the right-hand side, any functor from C to D and union actions on D. So there I take a pair, the functor S and some action theta. And on the one hand, I take S upper star T theta, which was this monad we constructed before using iterated cup fibers, and left con extension. Or on the right-hand side, we take our functor S. We have our action now, a union action theta, and we can take the K theta, which was the induced monad that was a comonad that was given by iterated fiber. And we do this composite like this. So we have these ways of constructing in a natural manner functors, monads on functors from C to M, or comonads on functors from C to M, from these maps from C to D and these actions. So we can even put sort of whole sequences of things together and look at towers of modules under C. And so in this context, we would have on the left-hand side intersection actions, on the right-hand side union actions. And then these maps have to be sort of appropriately compatible with the actions. I'm not going to explain the details. And that these triangles don't commute on the nose, but they're appropriate natural transformations. If they do commute on the nose, so much better, but that's not necessary. And so you can build, if you have these sorts of structures, these will be the kinds of towers that we'll be looking at in this context. That we'll call a category C tower intersection for these kind of objects I was just talking about, or C tower union. So that when we're having on the left-hand side, that should be C tower intersection, on the right-hand C tower union. Then we actually have functors that take towers like this of modules under C or with respect to either intersection or union, and the left-hand side will produce co-towers of monads or towers of comonads, and that'll build level-wise using these structures, these ways we had of going from modules under C to monads or modules under C to comonads, depending on whether we were looking at the intersection or the union structure. So here's the full pipeline, right? We have this category M equipped with weak equivalences and any small category. So we can consider either these towers with respect to the intersection monodal structure onto the PNs, or with respect to the union monodal structure on the PNs. And then we just saw that we can get from those towers to either co-towers of monads on the left-hand side, or towers of comonads on the right-hand side. We saw earlier that starting with a cotower of monads and an object, in this case, an object would be a functor from C to M, we can get a cotower, in this case, of functors and natural transformations, or an augmented tower of functors and natural transformations. And so this gives us two functors that will take a tower of modules, PN modules, and a functor, and spit out a tower of functors or a cotower of functors. So we have these functorial pipelines of ways we get from towers. So how does this all fit together to make a calculus and co-calculus machine for functor categories? So now we at least have cotower functors and tower functors. It's already in a very natural context, but does this really fit together into a calculus? So this is where it's going to get even more hand-wavy, because the conditions under which this all gives us a co-calculus or calculus is something that we have some examples of. We don't know yet what the very best way of describing the context is. So I'm going to do a bit of hand-waving. But the basic framework we need is that of a pre-calculus or a pre-co-calculus. So we start again with a category M with weak equivalences and some small categories. And we suppose we have one of these towers on the left-hand side of these intersection modules, or the right-hand side of these union modules. And we'll say the thing is actually a pre-co-calculus or pre-calculus. Each of these SNs, the SN is going from C to DN. And if this map from morphism from functor from C to DN has a right adjoint, we'll call it a pre-co-calculus. And if it's a left adjoint for every N, then it's called a pre-calculus. This gives us more control over what the left and right con-extensions are along these functors. That's the reason why that's important. So if our model, the category we're looking at, M, is actually nice enough, then for every pre-co-calculus and an appropriate choice of relevant functors from C to M, we're actually going to get a co-calculus when we apply this construction. So this was at the end of the pipeline. This was giving us, the pipeline gave us a way to start with one of these towers of modules and build a tower function. It turns out it's actually a co-calculus. If we start with a pre-co-calculus and we get a calculus, we started with a pre-calculus. Moreover, if we look at this calculus and co-calculus, we know sufficient conditions under which these things actually preserve are actually homotopy co-calculi. So if you start with a functor that preserves weak equivalences, it spits out a functor that preserves weak equivalences, and conditions under which the layers are homogeneous, which are again linked to conditions having to do with stability. So in the work that I did together with my partners in the Women in Topology project, we were inspired to think really about this dual situation of monads leading to co-calculus by work of Randy McCarthy on a dual calculus. So he was looking at dual calculus. He defined a dual calculus for functors of abelian categories. And it was defined in terms of what are called co-cross effects, which are dual to better known cross effects. And we were able to show that these co-cross effects actually do arise from these sort of intersection module structures. So module structures coming from applying Pn with respect to its intersection monoidal structure. So that they really were able to capture at least some well-known examples of both calculus and co-calculus using this general method of functorial construction of calculi and co-calculi. And with that, the end. Thank you very much for your attention, and I'd be happy to answer any questions.
Thank you very much, Kathryn. Questions? If you have questions, please come here and speak to the owl. Or tell anyone else to do that. Well, I actually had one. So you gave us several examples, simple examples of known towers. And then when you started talking about cubes, I thought you were going to talk about Goodwillie calculus or price calculus. Can you achieve that in that context?
So the Goodwillie calculus is something we really, really wanted to get it, but it turns out that this context is too rigid. So I think this framework is good for more discrete type calculi, algebraic type calculi. What the problem comes from the fact that it's really the comonads that we need are not going to be strict comonads. It's really going to be the kind of comonads one has in it needs to be something in more an infinity category context. One needs to move it out of the world that's too strict to something where you have plenty of room to do things up to homotopy, because any monads or comonads you have are actually going to be more like infinity monads, infinity comonads. So I mean, this is something I discussed with a number of people, and if somebody else would like to pick it up and try to do this properly in infinity category context, I think that then I'm pretty sure that you should be able to fit the Goodwillie calculus into this.
Any other questions? I think people are figured it out. Well, anyway, if there are no more questions, then let's start with Kathryn again.
Thank you.